Hello everyone, and welcome back to the continuation of our video series entitled Subnetting Demystified. My name is John Oden on the development team here at Boson Software. Thank you for taking a few moments to come back and continue with us. If you've been following along in this series, you've seen this graphic on the screen here several times, I'm sure by now, and this sort of charts our path through the series of videos that we've done so far, and the last one we did was video number 7, where we got into the mechanics of actually how to do subnetting calculations. Before we move on, I want to insert another video in this series that I've entitled down here at the bottom. You can see I've kind of added Class B subnetting, and we will refer to this as video 7A, Class B subnetting. And here's the reason for this. In all of the videos that we've done up to this point, all of the action has been in the last octet. You can see in the information that I've got up on the screen here, you remember that we used the color red to highlight the bits that were given to us that we cannot change. In this case, we were given the 192.168.10.0/24 network, so that means these first 3 bits, or these first 3 octets rather, which comprise the first 24 bits in this IP address, they cannot be changed, and I've highlighted those in the color red. We've done that for quite a while now. And then the remaining bits I've used either yellow or green, because we can manipulate all of these remaining bits. The last 8 bits, we could use some of those bits for subnetting. We could use some of those bits for host addresses. And we use yellow for our subnet bits and green for our host bits. And we're going to continue to do that. But up to this point, all of that has happened in the last octet. But it's not always like that, and we need to be able to do these same sorts of manipulations regardless of where the octet boundary might happen to be. And that's where we're going to go from here. We're going to do a few more exercises like this, but we're going to find ourselves kind of moving the mask back to the left. Instead of working with a /24, maybe we work with a /16 or maybe even a /17, and we're going to see what happens when these boundaries between the bits that were given in red that can't change and the yellow and green bits that we can change. We're going to see what happens when the dividing line between those doesn't necessarily fall on an even octet boundary. And we get into that when we start doing our subnetting back in the 3rd or even into the 2nd octet. So that's where we're going to go from here. Okay, so let's take a look at a new exercise, and this exercise is going to be one that we have not done before. This doesn't have anything to do with the topology that we worked on, where we took the /24 prefix and we chopped it up and we assigned certain numbers of IP addresses to the different locations. We're done with that. We've moved on to something new here, and you can see that I've drawn some binary up on the whiteboard in a familiar format, although you can see that the red and the yellow and the green, we're still using those colors, but we've divided things up here a little bit differently. So let me go ahead and put on the whiteboard the requirement. This is what we're given. This time, we are given the 10.224.128.0/17 network block. So that's what we're given to work with. Now, we're being asked to take this piece of the IPv4 address space, that's the 10.224.128.0 with a 17-bit prefix, and we're being asked to subdivide that or to subnet it so that we can have 50 different subnets with at least 350 hosts in each subnet. So that's our task. That's what we're being asked to do. So let's think in terms of host bits and subnet bits. If we are to accommodate 350 hosts, how many host bits will that require? Well, thinking back to our work with a /24 or a 24-bit prefix, which we used to call that a Class C, where the first 3 octets are fixed and we get to do whatever we want with those last 8 bits. If we make those last 8 bits all host bits, what's the maximum number of hosts that we could accommodate? Well, that would be 2 to the 8th, which is what, 256, and we have to take out those 2 special cases where we have all zeros for the subnet and all ones for the broadcast. So with 8 host bits, we could accommodate a maximum of 254 host IP addresses in that subnetwork. Well, in that case, we can see that 8 host bits is not going to be enough because we're being asked to accommodate 350 hosts. So what if we took 9 host bits. How many hosts could we accommodate there? Well, we could take 2 to the 9th, and if we do the binary math, we know that that would be a maximum value of 512 unique IP addresses. And notice the pattern here. If 2 to the 8th is 256, then 2 to the 9th is just twice that, or 512. So that's kind of easy, or a shortcut way to begin thinking about this. So with 9 host bits, we could accommodate up to 512 addresses, but we have to take out the 2 special cases. We have to take out the all zeros, which is the subnet ID. We have to take out all the ones, which is the broadcast. So with 9 host bits, we could accommodate 512 minus 2, or 510 addressable host IPs. So in this case, that will accommodate what we need. Well, you may say, well, we only need 350 hosts. Well, that's true. That's what the requirement asks us for. But 8 host bits is not enough. So 9 host bits is what we get. Even though we only need to be able to accommodate 350 hosts, it's either 256 or 512. There's no in between. So we're going to have a few extra host IP addresses in each of these subnets that we could use for expansion if we need to, or for some other things. Now, we need 50 subnets. So how many subnet bits are we going to have? Well, if we had 5 subnet bits, that would be 2 to the 5th. It's 32. That's not enough. We could do 6 subnet bits, which would be 2 to the 6th. That would give us 64 subnets, which is more than we need. And that's just going to have to do. We're just going to have to use 6 subnet bits, because here again, it's either 32, that's not enough, so that's clearly out. 64 is a few too many, so that's what we're going to have to go with. So anytime you've got a situation where it's not enough, then not enough is not enough. If you have a few extras, then that's just fine. Now, some of you may be looking over here at this idea of having 350 hosts in a subnet, and you may say, well, you really shouldn't do that because that's going to be a lot of broadcast traffic in one subnet, and you would be right. But probably what's happening here is that we are allocating 50 subnets with 350 hosts in each location. These literally could be individual office locations. So more than likely, these 350 hosts are going to be subject to further subnetting. So we'll take the piece of the IP address space that's responsible for those 350, actually a maximum of 510 hosts, and we could assign that to a given geographic location, and then the network engineers at that particular location may further subdivide that piece of the IP address space and break that down even further into different VLANs for different departments or different floors in the building or whatever. So when it gets down to the actual implementation, the actual number of hosts per subnet is probably going to be far less than 350. We're just breaking this down so that we can hand them out to different geographic locations where they could be further subnetted. So that's the premise that we'll go with here. So let's take what we're given and see if we can answer the by now familiar questions that we know we'll always need to be able to answer when we're working through subnetting problems. And that is, what is the subnet ID? What is the next subnet? And then the next subnet after that, we won't do all 50, but we'll do the first several so you can see how this works. So once we've identified the subnets, we'll need to be able to figure out what is the first host, what is the last host, and what is the broadcast for each subnet. So as we learned in some of our previous work, if you can just figure out what the subnets are, then it's really easy to figure out what the first host and what the last host and what the broadcast is, because if we know the subnet ID, then we know that the first host is just going to be the subnet plus 1. We know that the broadcast is going to be the next subnet minus 1. And then the last host is 1 less than broadcast. So if we can just start figuring out what are these subnets, then everything else falls into place. So what is our first subnet ID going to be? Well, we're going to do what we've always done. We're going to set all of the host bits to 0. So let's just assume that all of these host bits, these are the ones that are highlighted in green, we're just going to force all of those to be 0. And then we're going to force all of the subnet bits that we're able to manipulate to 0. Remember that that first bit in the third octet, we don't have access to that. That one is always going to be 1. So given that, if we set all of the host bits to 0 and we set all of the subnet bits that we have access to 0, then let's write out what is the first subnet ID. Well, I'm going to go write it. I'm going to write all 4 octets out here for the first one, and then we'll start filling our table out here. So we know that 10.224, that never changes. So let's go ahead and write that down, 10.224 dot. What do we get if we set all of these yellow subnet bits to 0? Do we get 0? Well, no, we don't, because remember, we've got to account for, when we write the value for the third octet, we've got to account for this first bit in the 128th position. Even though we can't change it, we still have to include it when we start to write out the values. So with all of our subnet bits set to 0, what is going to be the value of the third octet for the first subnet? That's going to be 128, right? And then with all the rest of the bits set to 0, 128.0, that'll be our first subnet ID, actually 10.224.128.0. That's going to be the subnet ID of the first of these 50 subnets. So what will be the value of the next subnet? Well, remember that all of these hosts, these bits that are in green, these are host bits, so they don't have anything to do with calculating what the next subnet's going to be, because to calculate the next subnet, we force all of these to 0. So what is the least significant subnet bit that we can increment to get the next subnet? Well, that's going to be this bit right here, which happens to be in the 2 position. Do you recall? In our previous discussions, we referred to this as the magic number because this is the increment. The magic number, or the subnet increment, is always going to be the bit weight of the position of the least significant subnet bit, which in this case is this guy right here, and he has a bit weight of 2, so that means that our subnet values are going to increment by 2. Well, why are they going to increment by 2? Well, because that's the least significant value that we have. The 1 bit over here, remember, that's a host bit. So when we're considering what are the subnet IDs, we increment by the value of the least significant subnet bit. So always remember that, and that'll help you as you go through these. So given that, what will be the next subnet? Well, if we were to set this bit right here to 1, and I'll go ahead and just draw it out. I'm going to write out the decimal, or the binary rather, the binary value for the third octet of the next subnet. Let me just write it out down here. So we said that all of our host bits for the subnet are going to have to be what? 0. So I'm going to write out 0.1, 2, 3, 4, 5, 6, 7, 8. Remember, that's a host bit. So now I'm going to increment to the next value in the subnet position. That's going to be a 1. We're going to set that one to 1. We're working in binary here. And then this value over here is already a 1 because that's what's given to us. We were given the 10.224.128.0/17. We're dealing with a 17-bit prefix here. That's the 17th bit, and it's fixed. So it's always going to be set to a 1. So we just have to bring that down. So we've got a 1, and then we've got 1, 2, 3, 4, 5 zeros. Remember, we've got this bit turned on here. So I wound up with a gap here. I didn't plan ahead too well, so let's just count to make sure we've got 8 bits here. We've got this 1 bit that's always going to be turned on because that's part of the network prefix. And then we've got 1, that's 1, 2, 3, 4, 5, 6, 7, 8. So that's all 8 bits of the third octet. So what's that going to be if we convert that to decimal? Third octet, that's going to be 128 plus 2 is 130. All of these host bits are 0, so we'll do .0 here. And then 10.224, that never changes, so we just write that down there. So if we know what this increment here is, then you don't even have to worry about doing the binary conversion to know what the next subnet's going to be. It's going to be 10.224. What? 132, right? And what's the next one after that? 10.224.134.0. And then the next one after that, 10.224.136.0. See, we're incrementing by 2 every time. 128, 30, 132, 134, 136. And the reason why we're incrementing by 2 is that the least significant subnet bit is 2, so that's the smallest. That's the increment. That's what the increment is going to be. We're going to be incrementing by 2s because that is the least significant subnet bit that we have. Okay, so to try to make this a little more clear, I've actually written out the first 5 subnets, and I've written out the last 2 octets in binary, just so that you can see how we're coming up with this. And why the last 2 octets? Well, because that's where the action is. The first 2 octets are not going to be changing at all, but the values in the last 2 octets will change as we increment through all of the hosts and through all of the subnets. So when we start writing out Class B subnetting, remember whenever we were working on our Class C exercises before, I was just writing out the last octet because that's where all the action was happening. So when I did this same table in our previous example, for the subnets, I would write out simply .32, .64, .96, or whatever, because the first 3 octets would not be changing. So to keep from cluttering up the table, I wouldn't write out the first 3 octets every time. With Class B, it's a little bit different here because we could potentially, and we will have values in the 3rd and the 4th octets changing. So I won't write the 1st and 2nd octet values out every time. But since these last 2 octets, the 3rd and the 4th, can and will change, I'll have to write them out, and I'll have to tighten up my writing here in this table and write the 3rd and the 4th octet every time. So how did we come up with these subnet values? Well, the first one, everything started at 0. We had all of the host bits set to 0, as we always do when we're calculating our subnets. And we started out with all of the subnets, or all of the subnet bits that we control set to 0, but we can't forget about this first bit in the 3rd octet because that's given to us as part of our network prefix. We're dealing with a 17-bit prefix, which means that the first 2 octets in their entirety are fixed, but we also have the first bit in the 3rd octet fixed. So notice as we go all the way down, it's always going to be a .1. So we've calculated the first subnet as 128.0 because that's what we get when we set all of the yellow bits. Those are our subnet bits when we set all of those to 0. But we have this red bit that we have to account for here, so we get the value of 128.0. And then if we look at the binary here, the next value that we could increment is right over here in the 2's position. Okay, we can't increment that guy right there that I'm waving my pointer at because that's a host bit. That's the first of the 9 host bits. So you got to keep in mind that in this case, the last bit of the 3rd octet is a host bit in this case. So we can't implement that. That's always going to be 0 because all of the host bits are always 0 when we're calculating subnets. So for the first subnet, all of the subnet bits, all of our yellow bits was 0. Then for the next subnet, we set the least significant subnet bit to 1. So if we take the bit weights and add them up, we take 128 from this most significant bit here, which is always going to be set to on. And then when we add to that this value right here, which has a bit weight of 2, so we take 128 and 2, that's the 128 right there and the 2 right there, we add those up and we get 130.0 as the value of the second subnet. What about the next one after that? Well, we turn the bit in the 2 position off because our next increment is going to then be to set the bit in the 4 position on. So if we take all of those bit weights and add them up, we take 128 plus 0 plus 0 plus 0 plus 0 plus 4 plus 0 plus 0. So that is 128 plus 4. That gives us 132 for the next subnet. What do we get if we increment in binary up 1 from that? Well, we can't change this last bit over here because remember that's a host bit. So what do we do next as we increment forward in binary? Well, we turn on the 2-bit and the 4-bit. The 128 bit is already on, so if we add up the bit weights, we've got 128 plus 4 plus 2. That gives us a value of 134.0 because remember all these host bits are set to 0. And then for the next subnet, we turn the 2-bit and the 4-bit off. We turn the 8-bit on. So now we add up the bit weights. We've got 128 for that bit. And then for this one right here, we've got 8. So 128 plus 8 is 136.0 for the next subnet. So you see how we did that? It takes a little while to get your head around it because you've got to keep in mind the fact that while we write these things out an octet at a time, we may have a host bit taking up a position in the same octet as our subnet bits, and that's exactly what's happening here. So that's why we can't increment by 1s, we have to increment by 2s because we gave that bit right there to the hosts. So the smallest increment we have is 2. So we're just counting by 2s here. And I drew out the binary so that you could see the first 5 subnets. Now I won't go all the way down through all 64 of them, but that's what the first ones look like. Okay, now that we have seen how to calculate the subnet IDs, we need to fill out the rest of our table here. And in our previous work, we learned that once we know what the subnet IDs are, then if we can figure out what the broadcast numbers are for each subnet, then it's pretty easy to figure out what is the first and the last host. So let's review the rules. Once we know the subnet address, 128.0, 130.0, 132.0, 134.0, 136.0, those are our first 5 subnets. We're told that we needed 50 subnets. We're using 6 subnet bits. That would accommodate a maximum of 64 subnets, so we're going to have some extras. We're not going to do all of those, but I'm just going to do the first several so that you can see how they work. So we saw how to do that. We did the binary over here. We saw how the least significant bit among the subnet bits dictates what the interval is. So once you know that we're counting by 2s, then you don't have to do all the binary, but we did it just to see how it works. So now let's figure out how to calculate the broadcast ID, or the broadcast address, for each of these subnets. Remember before that we learned that once you know what all the subnets are, then the broadcast for the current subnet is the next subnet minus 1. So when we were doing the subnetting before and everything was in the last octet, we had subnet 0, subnet 32, subnet 64, subnet 96 in our example, so that we could then just take 1 from the next subnet and get the broadcast for the prior subnet. So we had subnet 0 and then subnet 32, so we could take 32 minus 1, and the broadcast for subnet 0 was 31, right? And the next broadcast would be, 63, the next one would be 95, and so on. It works the same way when we're doing subnetting that involves splitting across octet boundaries, but the machinations are a little different, and there's a couple extra things that you need to keep in mind, but the underlying principles are the same. So let's go ahead and walk through this and see how this is going to work. I'm going to clear away some of the binary that we're doing here just to give some more room on the whiteboard, so I'll go through the first 1 or 2 here and do some binary so you can see what's happening, and then you'll see it's very easy to just do it without having to count all the bits. So let's go ahead and get started and see the example of the first one. Okay, what I've done here is I have taken the second subnet, which is 130.0 subnet, and I've written it out here in binary, and I've used the colors here to try to indicate that this first octet here has a decimal value of 130, right? And the second one has a value of 0. If we look at the binary side, I've got all of the bits in the second octet set to 0, or all of the bits in this last octet set to 0. This is actually the 4th octet within the context of the entire IPv4 address space. So this is the 4th octet. Everything is 0. This is the 3rd octet. We've got the 128-bit set to 1, and we've got the 2-bit set to 1. Everything else is 0. So if we had 128 and 2, we get 30. So that's our second subnet. We've determined from the rule that if we take the current subnet, which in this case I'm declaring that 130 is the current subnet that we're working on, 130.0. If we subtract 1 from that, then that will give us the broadcast address for the 128 subnet, and then so on down the line. So let's see what happens when we take 130.0 and subtract 1 from it. Once again, let me refer you back to when we were subnetting a /24. We were given that /24 back in our previous videos. And we had the 0 subnet and the 32 subnet and the 64 subnet. It's pretty easy to see that if we subtract 1 from that, whether we represent that in decimal or in binary, if we subtract 1 from it, it's 64 becomes 63 if we subtract 1 from it. But it's a little different here. I mean, theoretically, the math works exactly the same, but it's a little bit more complex because we're dealing across multiple octets. So let's go ahead and see how this works. And it works exactly the same way as when you're doing subtraction in the base 10 number system. You'll remember when you subtract, let's say you've got a value of, let's say 95, and you'd like to subtract 6 from that. Well, back in elementary school, we learned that if we wanted to subtract 6 from 95, we do it by evaluating each position. We've got the 1's position here and the 10's position here, right? So if we wanted to subtract 6 from 5, well, we can't quite do that because we go negative if we do that. So we have to borrow from the next position over. So we borrow 1 from the 10's column, and now instead of trying to subtract 6 from 5, we're subtracting 6 from 15, right? So what is 6 subtracted from 15? Well, it's 9. So since we borrowed one of the tens units from this second position here, instead of having a 9 here, now we have an 8. So if we subtract, and we're doing this in decimal, if we subtract the quantity 6 from the quantity 95, then we get 89, and we had to borrow to be able to do that. So in binary, it works exactly the same way. And let's go ahead and see it in progress. So now, instead of doing that in decimal, we're going to do it in binary, but it's going to work the same way. So we have quantity 0 in the ones position here, and we want to subtract 1 from it. Well, we can't do that because that would put us negative. So what do? We borrow from the position immediately to the left. So we're going to borrow from the 2's position. So if we borrow from the 2's position, we bring it over into the ones position, 1 2's unit becomes 2 1's unit, right? So if we subtract 1 from the 2 1's units that we have, what's the result that we get? We get 1, right? You see how we did that? Let's talk about it one more time. We're trying to subtract 1 from this entire 16-bit binary number here. That octet boundary, we're going to kind of disregard it because we just put that there for human convenience. Remember that when the data structure is inside the software that runs on your computers and routers and other networking devices, it's dealing with this as one big long 32-bit number. We're just taking the last 16 bits of it here because that's all that really matters to us in this case. So if we go through this bit by bit, we have a 0 in our ones position. We're going to subtract 1 from that. Well, we can't do that unless we borrow from the position to the left. So we're going to borrow a 2. We're going to bring it over into the ones column, so that becomes 2 1's, and we subtract 1 1 away from the 2 1's that we have, and that leaves us what? With this bit set to 1. So now we have a deficit in the 2's position. Now what are we going to do about that? Well, you guessed it, we're going to go over to the 4's position. We're going to borrow a 4, and we're going to bring it over here into the 2's position, and that becomes 2 2's. So remember, we have a deficit in the 2's position because we borrowed over into the 1's position. So this 4 that we're borrowing is going to become 2 2's. And since we have a deficit of 1 in the 2's position, we're going to take basically 2 2's and we're going to subtract 1 from that because of the borrowing that we did. So what do we get? We get another 1 right here. And that process is just going to continue. Now that we borrowed into the 2's position, we've got a deficit in the 4's position. So we've got to borrow 1 from the 8's position, and that gives us 2 4's, and we are short 1 4. So that's, now that we borrowed from the 8, we're 1 in the hole here, if you will, in the 4's position. So we borrow an 8, we get 2 4's. That cures the deficit, and that leaves us with a 1 value for that position. We're going to do the same thing with the 16. We're going to borrow from the 16. That's going to cure the deficit in the 8's position, and then that's going to leave us 1, so that bit gets turned on. Now we've got a deficit in the 16 position. We're going to borrow from the 32's position. We're going to take what we borrow and bring it right over here in the 16's position. So if we borrow 1 from the 32's position, that becomes 2 16 units. We have a deficit of 1, so that leaves us 1. Now to cure the deficit in the 32's position, you guessed it, this is just going to waterfall all the way over. We're going to borrow 1 from the 64's position. That gives us 2 32's. We had a deficit of 1, so that leaves that bit turned on. We're going to borrow from the 128's position to cure the deficit in the 64's position. So when we borrow from here, that becomes 264 units. We had a deficit of 1, so that leaves us 1, so we'll leave this bit turned on. So now we've got a deficit in the 128's position. So what are we going to do now? Well, remember that I said earlier that this octet boundary is really just for the convenience of humans and the way we interpret and deal with these IP addresses. But from the standpoint of the way the computer uses them, this is just one big long 32-bit number. So in reality, what that means is that since this is the 128's position, we start the counting over again at 1, again, just because we like to deal with these 32-bit values in 8-bit chunks. But in reality, this is going to be, if this is the 128's position, what is this really in the context of a 32-bit number? Is this not the 256 position? And would this not be the 512's position? And 1024 and 2048 and so on? Well, that's exactly what it is. So to cure the deficit in the 128 position, we borrow 1 from this 256 position here, and we bring it over, and now we've got 2 128's. We had a deficit of 1, so that leaves this bit turned on. So as we're doing this subtraction, we just hop right over this octet. We don't even really consider that because we're subtracting 1 from this 32-bit value. Actually, we're just dealing with the last 16 bits of it, and you'll see why here in a minute. So when we borrowed from the 256 position to cure the deficit in the 128's position, now that left us a deficit in the 256 position. So we're going to have to borrow a 512, which becomes two 256s. We were one short. We had a deficit of 1. So this becomes a 1 here, just like it did for all of these other positions that we've already done. But now watch what happens. Remember, we borrowed a 512 to fund the deficit in the 256 position, right? But look what we have here. We actually had a 512. So this is where the buck stops. We don't have to continue borrowing, because since we borrowed one from the 512 position to cure the deficit in the 256 position, that gave us this 1 right here. This bit in the 512 position was already set to 1, so we already had a value here. So we don't have to borrow anymore. This just becomes a 0, okay? And then we just bring the rest on down because we're done. 0, 0, 0, 0, 0. And then we bring that 1 down, okay? So this is what we get when we subtract a 1 from that 16-bit value of 130.0. So let's convert it back into decimal and see what it looks like. So if we have an octet with all of the 1 bits set on, what's that value? 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. I believe those would all add up to 255. And let's add these up. We had the 128 position over here. We have now a 1 position here. So 128 plus 1, that's 129. So there we have it. That is the value of the broadcast ID for the 128.0 subnet. So how do we do that again in broad terms? Well, we took 130.0, which is the next subnet, and to get the broadcast for the prior subnet, which is the 128.0 subnet, we took the 130.0 subnet and we subtracted 1 from it. So the broadcast ID for the 128.0 subnet is 129.255. It's actually 10.224.129.255 if you want to express all 4 octets, but you'll hopefully accept my shorthand here in that I'm only writing out the last 2 octets because that's all that's ever going to change. So let's calculate the broadcast for the next subnet. You'll see that I've reoriented the whiteboard here just a little bit, and you'll see that we now have the 132.0 subnet so that we can calculate the broadcast for the 130.0 subnet. Remember, we just used the 130.0 subnet to calculate the broadcast for the 128.0 subnet, so we always use the next subnet as the basis for configuring the broadcast for the previous subnet, because our rule states that we're going to figure the broadcast by taking the next subnet and subtracting 1 from it. So we're taking 132.0, or I'm still using the shorthand here, but let me go ahead and repeat 10.224.132.0. I'm focusing on the last 2 octets because that's all that's changing. So the 4th octet we have 0, and that equates to all of the bits being set to 0. In the 3rd octet we have 132, so we're going to have the 128-bit turned on and the 4-bit turned on. So 4 plus 128 gives us 132. So this shows you what the binary looks like for the 132.0 subnet. So let's do our subtraction, and just like we did before, where we have to start borrowing from the column to the left, we take the quantity 0, we subtract 1 from it. So because we have a deficit there, we have to cure that by borrowing from the 2's position and carrying over into the 1's position. That gives us 2 1s. We subtract 1 from that, and that turns that bit on, and then everything just waterfalls over. We borrow from the 4, cover the deficit in the 2's position. That gives us a 1 there. We borrow from 8 to cover the deficit in the 4's position. Just like we saw in the previous example, we go all the way over and we get to the 128's position. So to fill the deficit that we now have in the 128's position, we have to borrow from the next bit in the next octet, which, as we saw in our previous example, is really the 256 position, because this is all one big long 32-bit value. So we've borrowed from the 256 position to cover the deficit in the 128's position. Gives us a 1 there, so now we have to borrow from the 512's position. So we take 1 512, bring it over into the 256 column. That gives us 2 256's. We were already down 1. We had a deficit of 1 256 value. So we carried over 2, and that gives us a 1 there. So now we have a deficit in the 512 position, so we cure that by borrowing from the next position over, which is the 1024 position. So we borrow from that value, bring that over into the 512 position. We were in a deficit of 1 in the 512's position, so we bring 2 over, and that gives us a 1 down here. We don't have a deficit in the 1024 position because look right here, 132.0, that gives us we have to have this bit right here, the 4-bit turned on to give us the value of 132. So when we take away from the 1024 column to fund the deficit in the 512 column, we don't have to borrow anymore because we already had a 1 turned on in the 1024 column, so that 1 just becomes a 0. There is no deficit at this point, so the borrowing stops, and we just bring everything down all the way across. So that gives us, in binary, we have 1s all the way across, so we know from past experience, if we have an 8-bit binary value where all the 1s are turned on, what does that give us? What does that give us? That gives us 255. If we add all of those 1s from 128 all the way across, that adds up to 255. So we've got 128 plus 2, that gives us 130, plus 1, that gives us 131.255. So the broadcast for the 130.0 subnet is going to be 131.255. So I've cleaned up the whiteboard, and based on what we have learned in our previous few steps that we've done, we have seen how to derive the subnets, and we had that already, 128.0, 130.0, 132.0, 134.0, 136.0. We just went through the binary math that was required to derive the broadcast addresses for each subnet. Remember, we took each subnet and we looked at the next subnet and we subtracted 1 from it, and we just saw how to do that. And here are the values that we came up with for the broadcasts. 129.255, 131.255. And we just did the binary on those first 2, but you can see the pattern, and it just continues. 133.255, 135.255, 137.255. We could write out a couple of more subnets, and now that we've seen the pattern, we can just do it in our head without having to go through all the binary machinations. Our next 2 subnets would be 138.0 and 140.0. And the respective broadcast IDs would be 139.255, 141.255. And then given that, it's very easy to determine the first and last hosts for each of these 2 new subnets we're now considering. We just take our subnet and we add 1 to it to get the first host. So our first new subnet, 138, the first host would be 138.1. We already had the broadcast of 139.255. We subtract 1 from that and get 139.254 as the last host in the 138.0 subnet. Same thing for the 140.0 subnet. First host is 140.1. We calculated the broadcast of 141.255, which gives us a last host of 141.254. And so it goes, and you could walk all the way down through the remainder of all of those 64 subnets if you wanted to, and it's going to work the same way for every one all the way through. So a couple of things that we should consider before we leave this particular exercise is that we've seen how to derive the subnets and the broadcasts, and from there we can get the first and last hosts in each of these subnets. What is going to be the subnet mask that we would associate with each of these subnets? Well, we could express that in a couple of different ways. We're given a 17-bit prefix to work with here, so that means that from this line to the left, that all remains the same. That's what's given to us. This is what we have to work with. From this line to the right, then we can allocate these remaining bits as either subnet bits or host bits, and we chose to take the first 6 of those bits and declare that they be subnet bits to give us sufficient bits to derive the 50 subnets that we were required. We actually could get 64, 2 to the 6th, the 64. And then we have the 9 host bits. So the new dividing line between subnetwork and host is going to be right here, right here. So what is going to be, let's first figure out what is going to be the prefix length for these new subnets. What we were given is /17. So if we just move the line over by 1, 2, 3, 4, 5, 6 subnetting bits, what's that going to be? It's going to be a /23, right? So we could write out 10.224.128.0/23. That's our first subnet. Guess I should have wrote that down a little bit. Our next one would be 10.224.130.0/23. and just right on down the line. So what would be the decimal subnet mask that is the equivalent of a 23-bit prefix? Well, that would just be if we set all of the bits to 1 up to the point just before the host bits start. So if we wanted to calculate what is the decimal subnet mask that would be the same thing as a /23 prefix, then we would set the first octet to 1s, all 1s, the next octet to all 1s, and then we would configure all 1s in the third octet up until just before the last bit. So that would be right there. That's where the 1s would stop and the 0s would start. So how would we write that? Well, the first 2 octets are easy. So it'll be 255.255. something. So let's figure out what the something is going to be. What the something is going to be is in the third octet, we need to set all of the bits in yellow to 1. Now this first bit in the third octet, that's already set to 1 because of the prefix that we were given. So what would we get if we added up the bit weights of all of these bits in yellow? So we take 128, we've got to account for that one. So we add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2. What's that going to be if we add it all up together? Well, maybe it's easier to just work backwards. If we had all 7 of those, or excuse me, if we had all 8 of those bits set to 1, just like it would be with a 24-bit prefix, it would be .255. Well, it's not. It's 1 bit less than that. So it's going to be 254 would be the subnet value in the third octet. What would be the subnet value in the fourth octet? Well, we've already forced this one to be 0, or we've declared that this one has got to be 0. So it's that, right? So the subnet mask for this /23 would be 255.255.254.0. So if we were to pick one of these subnets, and if we were to hand it off to the network administrator at one of the locations that we're going to assign, let's say the 136.0 subnet to, so we could simply write, just for example, I'm just picking one out here, 10.224.138.0 with a 255.255.254.0 mask, or we could write /23. That's exactly the same thing. It's just 2 different ways of expressing the same value. One final point before we wrap up this particular exercise and move on. I'm going to ask you a question. This is a bonus question, and I want you to consider carefully before you answer. Take a look at this. I've written this IP address on the whiteboard, 10.224.135.0 with a mask of 255.255.254.0. Now we just went through the steps to figure out what the subnet mask should be on these subnets that we have created by taking the /17 prefix that we were given and chopping it up into the /23s. A /23 is the same, we learned, as a 255.255.254 decimal mask. So my question to you is this. Is 10.224.135.0 an invalid IP address, or is it a valid IP address? Now think carefully about your answer and go ahead and hit pause and scratch your head for a minute and think whether this is or is not a valid IP address, and then when we come back we'll work through and determine whether it is or it is not. To work our way to the answer, the first thing that I'll remind you is the rule that says that if we have all of the host bits set to 0, then that is the definition of a subnet ID or a subnet address. And most folks, when they begin to learn subnetting, they start with the smaller subnets where everything is contained in the fourth octet, and we break things up into maybe a mask of 255.255.224. That would be a /27, and we get subnets that are like .0, .32, .64, .96, and so on. And we are conditioned to learn that anything with a 0 on the end is probably a network address of some sort, or a subnet address of some sort, I suppose I should say. But is that always true? Well, to get the answer, let's go back to the binary. Anytime you have a question about any of this, and this is why I've been very methodical and very rigorous as we go through this to show you how it works in binary, so that when you run into some of these edge cases that you may not be exactly sure of the answer, you can always fall back to working it out in binary and being able to arrive at an answer in just about every case. So remember the rule. The rule says that for it to be a valid host address, some of the host bits, at least one host bit, has got to be set to 1. We can't have a situation where all of the host bits are set to 0, because that is the definition of a subnet address. So to get our answer, let's write this out in binary. So up here we have the binary. I started with the fourth octet, which is 0. That's easy. All of the bits are set to 0, so I wrote those out there. In the third octet, we have the value of 135, so we need a 1 in the 128 bit. As it turns out, we'll always have a 1 in the 128 bit because that's part of the 17-bit prefix that we were given. So we've got 128, and we've got 4, and we've got 2. So if we add 128 and 4 and 2, what do we get? We get 134. And then we have this last bit set to 1, which gives us a total of 135. So now if we examine the bits, the answer becomes clear, and we find out that this is in fact an absolutely valid IP address, because even though the last 8 bits are set to 0, this bit right here, which is the first host bit that's over in the third octet, is set to 1. So if we look at the green bits here, if we have at least one of those green bits set to 1, then that is a valid host IP address. And in this case, 10.224.135.0 with a 255.255.254.0 mask is in fact a valid IP address. So you got to be careful with these edge cases, particularly when you get into the larger numbers of hosts, where you start getting some of the host IP addresses, or some of the host bits rather, over into this third octet. You can find some situations where you'll wind up with a 0 in the fourth octet, and that is in fact a perfectly valid host IP address. So be careful with that. That's kind of a good, this is some good fertile ground for tricky exam questions if you happen to be taking certification exams. So be aware of situations like this as you do your studies and preparations. So that about does it for this video. Thanks for spending a few more minutes with us, taking a look at this idea of Class B subnetting, and this is where the subnet bits start to appear over in the third octet. Notice that while in principle everything is the same, the actual mechanics of working through these things change just a little bit. There are a couple of things that you have to keep in mind when you're working with these larger subnets that have more than 254 hosts in them. So we've seen some cases here. If you have any questions about what you've seen, remember the comments. We keep an eye on this, so just put a comment down below if there's something that you have a question about, and I'll be glad to follow back up with you and get you an answer to your questions. If you have found that this video series is helpful, we would appreciate it if you would subscribe to our channel and click like down below also if you found these helpful, and that'll make them more visible to other folks who may find them helpful as well. So once again, thanks for checking out our video. Stay tuned for the next video where we're going to extend these ideas and see how to speed up this process. If you were to work through these, and if you have worked through these examples, you can see that it takes some time to work out the binary and to draw the bits and do all that. And if you're under the pressure of time, particularly in an exam situation where you're doing a certification exam that requires you to have some subnetting skills, you're not always going to have time to be able to do all that. So you're going to need some techniques to allow you to speed things up, and that's where we're going to go in our next video, which is entitled Fast Subnetting. So be sure and check that out. Thank you.